take the stage and start this session. Thank you so much. No, 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 no. This now charge to you. You call them and they will present. No, no, no. This is your job because you are session chair. Thank you. You are the boss now.
Assalamu alaikum and good afternoon. Welcome everyone for this afternoon session. I would like to call for first speaker, Mr. Muhammad Munir, to speak about his paper is Date Palm Derived Biochar Amendment in Mitigate Water Defect Effect in Greenhouse Grown Cucumbers. Please come, Mr. Muhammad.
Assalamu alaikum. This is Muhammad Munir from King Faisal University, Al-Ahsa. It's a great honor and pleasure being here at this conference. Today, my topic is date palm derived biochar amendments to mitigate water deficit effects on greenhouse grown cucumbers. This is, sorry. Yeah, thank you very much. Thank you. Yeah, so we're going to start the motivation of our project about the biomass recycling and about the biochar. Since yesterday, we have heard a lot of about biomass, which is generated through forestry and agricultural practices. So a lot of biochar is produced through agriculture and forestry cultural practices. And we know the biomass waste, which I learned yesterday that this is not a waste, it's a recycled material, sure. So the biomass recycled material production is around 140 to 146 gigatons per annum, which accounts for a very good 14% of energy consumptions. And agricultural biomass is possibly a foundation material to produce sustainable energy that depends on the type of feedstocks and crops, different material, the leaves and twigs and the stems. For example, rice straw has an energy content of around 13% megajoules per kg, and hay grass around 16 megajoules per kg, and the date palm we have around 14.4% megajoules per kg. Most of this biomass recycled material are left to decompose in the field, which take more time because it contains cellulose, lignin, and all these sort of material which take time to decompose. Or the farmers, the date palm farmers, they just burn it in the field. That cause certain environmental pollution sort of things like carbon dioxide if they burn it, or methane if they leave it to decompose, and nitrous oxide as well, which is a greenhouse potent gas. So we talked about a little bit about biomass, and then the date palm, we're talking about the biomass of date palm. So it is cultivated around 1.25 million hectares worldwide, globally. And its leaves, stems, fruit, bunches, and leaf sheets, seeds, they all are like a leftover material. So it has a great potential to recycle it, to reuse it into different sort of things. So a date palm tree is estimated to produce around 20 kg. I have learned yesterday that it's around 20 to 30 kg per year, dry matters. That is excluded 10% of wasted seeds. Saudi Arabia, we know it produces more than 200,000 tons of date palm waste annually. So there is a lot of potential. This statistic is around 2018. So maybe it is updated to more than that one. So the limited amount of date palm biomass is utilized as a fodder, not 100% like a fodder, but it mixed with some other crop biomass and then used as a fodder, or converted into compost, or a raw material in pulp, paper, and chipboard industries. They use it. So date palm biomass, we know it has cellulose, hemicellulose, lignin, and organic matters, volatile solids and low moisture content. So these property made it very ideal to recycle it. So we knew about biomass, date palm waste, and now thanks to the various thermal and biochemical technologies, they emerged to convert the energy stored in the biomass into its useful form. The thermochemical conversion processes, there are different processes like pyrolysis, like gasification, combustion. These processes are used to produce biochar or synthetic gas and biofuel and many more. Now we come to the biochar. So biochar is produced through pyrolysis. So in a controlled temperature condition, in a furnace or in any prototype material which we have used, I'm going to show you in a minute. So we use this biomass material in an anaerobic condition where oxygen is very limited in the chamber, and the process we use is pyrolysis, which is the thermal decomposition of organic material, where we elevate the temperature, we raise the temperature with a limited oxygen in atmosphere, limited oxygen level. So what we produce, the biochar. So when we produce, it depends on different feedstock available. So if you go through the literature, you will see some material they use around 250 degree temperature, and some material which is very hot, so they increase the temperature and they play with the pH, lower the pH level or EC level. So normally equal or less than 300 temperature. So at that temperature it is reported in the literature that most of the nutrient are like sustained, they are available within the biochar content. And if we increase the temperature equal or above 600 degree Celsius, that reduce the nutrient contents and increase pH as well. But it is not, there is no hard and fast sort of things that we have to play with the material, which our feedstock we have, and then we see which is appropriate. That's what we have done with the date palm. Well, I think we, since yesterday, we know about that this is a carbonated material, the black, hang on. Yeah, it's a black material. It's just hindering me. It's a, it's a black carbonic material which stay like longer in the soil. It retain micro and macronutrients. And I would show here a quite rosy picture of biochar rather than to say its limitation. There are some, of course, limitations, but I'll just like to show a rosy picture that it has advantages in carbon sequestration, agriculture, and environmental sustainability. So the carbon sequestration, we can sink carbon for a long time in the soil, right? So that is we can mitigate the climatic change. I mean, if it is outside decomposing material, burning it, then it affects the climate. The other thing is that biochar improves soil water. The biggest advantage is water holding capacity. It increases. It retains nutrients, recycling nutrient materials. So improve soil microbial activities. A lot of things they already mentioned yesterday. And highly porous material, we know that it enhances soil fertility. If it is porous, you know, the nutrients sustain within the surface area. The microbial activity is, you know, enhanced there. So the soil fertility increase. So, and then this is the advantage of date palm biochar. I can assume it. The biochar can use to acidic and highly weathered tropical soils to raise pH, because that question arises like yesterday. Someone asked in room C that, you know, how can we play with its high pH level? So that why if we are not going to reduce any pH, we can use it in acidic soils. Like I would put example here, like British soils, they are more acidic. So I had an experiment there on this zucchini. So we used this material, the date palm material I took from here. I did analysis thanks to Dr. Rafzan Hajouj. So he supported us, and we had done this zucchini experiment there. And acidic soils, because the soil pH is acidic there in Britania climate. Temperate, you know, a lot of rain there, lot of organic matter is there. When there is more organic matter, the soil is acidic, and rainfall as well. So decomposition is very rapid. So this date palm high pH is around 8 plus 7.8 like this. So if we use it in acidic soil, it is ideal. It reduces the soil, rather increase the acidic pH to the neutralized level. Or we can play it with another way as well. We can mix this material with the organic matter, any organic compost available which is acidic. We can mix it with it, and we can use it for any cultivation. And another thing is, we're talking about the organic material. If another experiment I have done, because this is, we went on the applied side of the because a lot of theoretical studies have done. If we mix it with the animal slurry, even like animal urine that is acidic, so we mix it with the urine. I'm not going to mention the name of the animal. We mix it, and then it improve or decrease the pH. It's neutralized, and that we activate, made activation. Activated biochar, we use it, we treat it with urine. We use it for flower production, like snapdragons, chrysanthemum, and others. So we quite few ornamental plants, we use it, and it gives us very good results. So this is the ideal one that we can, it can be used in acidic and high weathered tropical soils, rainfall and all these things. So Or like I said, the next one is the biochar can be used as a soil amendment in mix up with, conjunction with compost. So another organic material or slurry. Like I said, with the urine, you mix it up and leave it for a couple of months, and then it will neutralize the pH, or even with the fertilizer. So it retains pollutants. We are nearly to have an experiment of this the retention of lead and cadmium and pesticide, heavy metal. These are, they have storage ability. Structure is improved, stability of the nutrient is there, and then it retains nitrogen, like it has a porous spaces. And when it retains nitrogen, that means the nitrous oxide gas is not releasing into the atmosphere. So that means you are going to mitigate the climatic effect as well to some extent. And again, it also retain or reduces the methane gas, because when when the biomass is not going to decompose, when it is decomposed, the methane is released. You are not going to decompose it, so you are going to carbon sequestration for a long time. So you are burning nitrogen for, like in the literature, it's like 1,000 years. You can bury nitrogen like a Amazon forest. They are for thousands of years, the soil is all black because of these things. Right. So at the end, the biochar, we know that it's a simple process, it's a sustainable tool for recycling and managing the agricultural waste. We talked about biochar, its utilization as a biochar, and now we come to the kingdom. It has a dry land, sandy soil, right? Sandy soil, we know that cannot retain much moisture. Alkaline, of course, the pH is above 7. Low organic matter, because rain is not there. There's no weathering effects. There is no vegetation on the soil. So that's why the organic matter is poor. So all this makes poor water retention. So we need something to improve water holding capacity of the soil. And we know this, that KSA is among one of the water scarce countries. So here water is precious. And whatever the water is available, 87% is going to utilize in agriculture industry. So we have, if we are going to amend soil, we are going to reduce water consumption. Then come to the climate, which is temperatures increasing, why increasing, carbon dioxide and all these greenhouse gases are going into the air, increasing overall temperature. So we have, if we are going to concentrate on CO2, methane and all these gases, we can lower or reduce this effect. So what is happening? We are going to have a longer droughts, extreme weather conditions. So this also giving us a motivation to have a low carbon pathways to mitigate our this climate damage. So all these things, the biomass is available, the technology is there. We can make, in this case, biochar, biomass, biochar. We have a scenario in front of us, and that is the kingdom where the soil is sandy loam, water is scarce, and globally we know that the climatic change is going to happen. So we have a good rationale for our study to have all these components in front of us to use biochar on applied side. So we put these three major objectives in front of us, that we have to, first off, we got muffle furnace, we can build biochar, lot of studies shows that, but what we have done, we built up a prototype furnace. I'm going to show you the furnace picture, and thanks to one of our program, Dr. Majid, head of the program, so he made the furnace. So that was one of the objectives, that we have to have a prototype furnace. And then we have to determine the quality of the material, the biochar material. What is the quality of that material? Is it usable or not? What are the pros and cons of that material we have? And then we have to use it like on applied science thing. Is it a usable material, whatever we have? Because since yesterday we talked about there are some like pros and cons with this material. So we try to use it to study its morphological parameters, physiological parameters, and biochemical parameters using this cucumber crop. So our study, they comprise of these two components. We build up a prototype furnace, and then we applied the biochar derived from that furnace. So here we are, the furnace. This is a schematic diagram. Again, thanks to Dr. Majid, head of Date Palm Engineering Precision Technologies program, and we have mentioned this one in one of our papers, where we use leaf biochar, stem biochar, and the soil, which was sandy loam. Just couple of pictures. That furnace we use. Feedstock we use leaf and stem. Here, thanks to Dr. Ghazavi, he really helped us to have this material. So how we produce biochar? So this is a small scenario that we got this residues from, we left it in the field for this hour, we chopped it, and we further dried it at 60-degree temperature, and then we placed it in the prototype furnace. We had different temperature experiment, and then we came to a point that this 300-degree temperature for 2 hours is where the pH is not very high, and we can play with the pH, and EC as well. So that's why we choose 300 temperature. So we received this black carbonized material, and then we left it room temperature 24 hours, and after that we meshed it and stored it in a sealed container. You can see here the scan electron. This is our material we use. In the bottom is SEM pictures, couple of. You can see a lot of pore spaces, quite good pore spaces where they retain nutrient, macronutrient, and microbial activities is there, moisture is there. So this is very ideal to use it. Another couple of things, the fronds, leaf fronds, you can see the pictures, and then the powder form. Here we can, it's worth mentioning that we have ordinary biochar and activated biochar. We activated our biochar. Since like yesterday, people talk about the used biochar, but I think they didn't talk about the activated biochar. The beauty of activated biochar is it lowers the pH, it neutralizes the pH. So like I said before, you can treat it with any acidic material, whether it is soil, like I put an example of British soil, they are acidic. So we used that one there and results were very good on zucchini plant. And we treated it with celery. I'll mention it here, I use the pig celery. So here I want to use camel celery. So then we want to see, and we treated the date palm biochar with the pig celery for 3 months. We activated it, right? So it lowered because the material was acidic. So this has high pH, alkaline pH. So we mix these two things up and leave it for a time, and then we use it for flower production. Like I said, in Trinum, we got a data for that. Fantastic, we can use it. And we had a analysis of that material as well. And we had an analysis from Yara. Yara is a very good company in Britannia. You just send them the material and they will screen out all the profile. So, okay. Anyway, this is how we treated here. It's this already published material. Phosphoric acid we use, and that is a procedure available in the literature. So that is what we use in their King Faisal University this year. Design we as a 2 factorial design. Why 2 factorial design? We had 3 like a feedstock. We can say 1 soil, 2 feedstock, leaf biochar, and different field capacity, moisture content, 100%, 80%, and 60%. So this was the little bit crop husbandry. So we got the variety from Britannia, and then we in a growth chamber we got plants, true leaves. We move them, transfer them, and then we use 5% volume by volume. Yesterday that was another question. Volume by volume. Someone mentioned that weight by weight. I tried that one, but no result. To be honest, it increased the pH, and then we use volume by volume, 5%. Okay, this is a little bit the analysis of the data, the solar radiation within glass house, temperature, relative humidity. So these are the parameters, the morphophysical parameters. So these are just a couple of pictures we have done. The results, results we have got? How much time, Doug? Time? Yeah, okay. So I'm sorry. Yeah, I'm sorry to say that I have 3 things here just to save time. We have graphs, we have a heat map, and we have a correlation thing. So we can see here that, if you see the blue line is control, and then the orange is leaf biochar, and the gray one is stem biochar. So you can see that all these parameters, what we have, what we have is, thank you very much. We have like a vine length, stem diameter, plant spread, or days to flower, days to fruit set, maturity. So you can see all these, the red mean the time or the data is higher, and the green is lower. I mean, there is a legend on the heat map as well. So you can see the correlation. You can see some has like around 1% or 98, 91, 99%. So quite good correlation between the variables. We can see here that the stem biochar mostly at 10% field capacity higher. But quite few, we can see a promising results when the temperature, when the field capacity is 80 or 60. If we compare 80 and 60 in the control, is much lower figures or like negative figures, and still wherever the field capacity, the moisture content is 80% or 60%, using leaf biochar or stem biochar is much better results are there. So I mean it is, you can see it. So the next one is like leaf numbers, leaf area, we focused on the leaf. The leaf area index, and specific leaf area, and leaf dry matter content, and leaf thickness. Leaf thickness actually was our main variable. That's why we consider, because to calculate leaf thickness, we have to calculate the specific leaf area and the leaf dry matter content as well to get that the models for leaf thickness. So leaf thickness is showing wherever the leaf biochar is followed by the stem biochar. You can see on the heat map the red, so the value is higher than the other, and you can see easily the correlation is leaf thickness, leaf numbers, all these leaf area, there is a very good correlation of these parameters. The next one is our gas exchange system. So we have recorded chlorophyll content, photosynthesis, stomatal conductance, intercellular CO2 concentration, and transpiration rate, and water use efficiency. So we say here, there are two clusters here which are like water use efficiency and CI. They are like have one group of correlation. The rest is with the gas exchange, the photosynthesis, and the evapotranspiration. So all these characteristics, if we see, they are much better. All, like wherever we use stem or leaf biochar, 100% field capacity, and still the result is much better than control, which has got 100%, the control which has got 100% field capacity. So using leaf biochar, stem biochar at 80%, 60%, they are also giving very promising results. The next one is the number of fruits per vine, the fruit length, diameter, volume, and fresh weight, and the yield per plant. So they are like, if you see the correlation with the factors, I mean, obviously these factors correlate because these are the yield components. So they correlate, which is positively correlate. So we can see their relationship here. And then again, they are far from better, with comparing to the control. The heat map, you saw, leaf 100%, all red, higher rate, and stem biochar 100%. Also, this is morphological. We have dry matter partitioning. So if you see the fresh weight, dry weight, stem, leaf fresh weight, dry weight, and the root fresh weight, dry weight. So you all see much better. There are correlation with the variables, and their interactional performance is much better through the graphs. The next one is the color one. We also try to, because very limited literature is available, the effect of water stress on the color of fruit is on edible fruit, but not cucumber vegetable, which is not botanically, but we use it as economically a vegetable. So we recorded its color as well. So its lightness is green to red color, and then blue to yellow color, chroma, hue angle, and delta C. We recorded all these things. They are much better as compared to the stressed plant in control. Last few, no. Yeah, that is, yeah. Last one, yeah. This is the fruit firmness, right? Which, correspond to whatever it should be at high level of moisture available and at low level. So we can see here as well, where there is more moisture content, the fruit are like a soft, the firmness is reduced, and all the pH of the fruit, the total soluble solids, the total sugar content increase where the more water is available, and the proline content is also a very good indicator. When there is a stress, the proline content increase to show that to give a to trigger the plant that you are under stress, right? And the fruit surface area we have, and the relative water content, which is also essential to know that how much water content retained at different stress levels. Yeah, this is the last big picture of the correlation. So we can see here, like we divided it, very obvious that we divided it into two hierarchical clustering. So we can see one is with the color and different water use efficiency, and these parameters, they are in one cluster, and the rest of main of the cluster on the far end side, all these parameters, variables, they are in a second cluster. It's a big chunk of clusters, they correlate to each other. This is the core diagram. To be honest, our subscription was finished, so we will complete it in our paper. So the conclusion, just last one, we made we have done the prototype furnace. We have done, we got the leaf stem biochar, and we evaluated its properties. Nice one. So we concluded that although 100% field capacity we maintained in sand and leaf biochar, stem biochar, they were superior. But still, if we maintain that capacity, field capacity within using these material, we have far better results than in the control factors or whatever it was. So we improve yield and things like that. And so the last one is that we can, still there is a window to use 80% or 60% field capacity, where we can save 20% or 40% water. And in this, where the water scarce, in the climate where water is scarce, we can still, it's a 20% or 40% lot of water. We can save it at a very little expense of morphophysiological and biochemical properties. So we can compromise at one point to save this matter, so it's not going to make a big difference. Yeah, thank you very much, sir. Yeah, you take this one. Okay. Sorry, I think, yeah.
Thank you very much, Professor Mohammed Munir, for your presentation now. I think we are running out of time, but we still can maybe take two questions, short questions, please. Any question?
Thank you, Dr. Munir, for your presentation. My question, I ask about the relationship between temperature and time for preparing biochar. You said 300 temperature is good. If we increase that effect in the biochar properties?
I mean, yeah, I think you were the part of that thing. Yeah, we increase it, and we've seen that, it affect the nutrient content of the plants, the pH increase. So that's why we maintained it. It was, it was 7.8 or whatever in the properties. So we tried to, we had that pH when we treated it at 300 at that specific time, 2 hours. We played with this. We increased the time, the temperature, and then we saw that, is not, it is increasing the pH and reducing the nutrient content. So we just stick with at that temperature and that time interval, the 2 hour. So and then we activated it. We found a way to activate it to further reduce the pH. You were there with me. So we played with the black material all day, washing it up and blah blah blah. So and then counting the pH, so reduce it. But I think, if you don't want to dirty your hands, use organic material and play with this rich in phosphoric, the urine thing, the camel urine or animal urine, celery even, liquid celery, not the solid one, because liquid one take less time to activate your biochar. So if you play with that material, you can reduce pH. You can, if you have a nutrient content evaluation, you can see if it is good, 2 months, 3 months, whatever, depends on the material, whatever the biomass material you have. You prepare the biomass biochar from that one. So it's a kind of, yeah.
Second question, you see this production of biochar is economically here, مثلا, as in Saudi Arabia, because the pH play a big role to add it in the soil?
The thing is, again, Doctor, I think you are going to with Dr. Majid, and you will include me as well, to reduce the cost. When the feasibility of application of this material is a major question mark. So if we use like solar energy, so Dr. Majid is, so solar energy to convert this material, it may take more time, but we can reduce the cost. At this moment is okay. It's a science we are playing with, right? So maybe this could be a pioneer research, and then someone like playing with the solar radiation and things like that, reduce the cost and make it more applicable.
Okay, another last question, maybe.
Thank you so much, Professor Munir, for such a nice presentation. I'm Dr. Mukarram from Imam Abdul Rahman bin Faisal University. Related to I'm concerned that did you find the textural properties of the biochar you have produced?
No, I'm sorry, no.
So because you have shown the scanning electron microscopy,
yeah.
So I'm concerned about the pore size.
Yeah. We were interested to find a difference between activated biochar, because when you activate it, you have a more pore spaces. Exactly. The size is increased, surface area is increased. And we also had that one of the objective, that when it is in the literature that it increase the surface area. So, but that one was ordinary. We requested, I'm not going to say anything else, that we requested to use that material, but we failed. But we'll try our best to have a proof that it really increased the surface area.
Okay.
Yeah, but I'm sorry, we didn't do that.
Okay, thank you.
Yes. Yeah. Thank you, Dr. Munir. Actually, regarding the pH reduction, and using the urine. Urine by nature, it is alkaline and it has ammonia almost.
more.
And are you going to sterilize the urine or you use it as fresh? And you say that activation period is 3 months. Even with the 3 months, urine pH will be higher. Then I pretend this will not be the proper solution. I would advise, as a soil scientist, to reduce the pH, you have to add gypsum. Gypsum will add calcium, and the sulfur will reduce your pH in the soil as well as in the biochar. Thank you.
I just mentioned here just one thing. I used not gypsum, but I used sulfur in a laboratory experiment. I used sulfur, and that is also taking long time, doctor, to get like in that desirable pH. But that thing, like you said, that idea came from one of the grower there in Britannia. I used to work with a satellite GIS company there called Soil, SOIL. So they scan, using GPS technology all in UK. So I talked to the guys, what is the possibility? And they said that we are using this pig urine for 6 months, for 3 months to get it neutralized. So I got that idea from there. So I used that one, right? And another maybe, because there is always rain. That may be, if because you are just mixing that material and leaving, in the field and just covering it with some sort of cloth or something. And then after like 2 to 3 months, I took the samples. I sent it to the Jara company, it's a big company. So I asked them to analyze it because that was the environmental material. So they like has in the properties, all the heavy metals, they scanned the nutrients and all the pH, all these things, and it was like audio 7.8 or something it comes, or 7.4. We have to compromise with the phosphorus or a couple of more nutrients while using this biochar, because at little bit high pH, they are like, not very available things.
Thank you.
So, but like you said, yeah, we can, use gypsum or sulfur. I am playing with sulfur, sir. Yeah, because acid definitely reduce the pH and obvious. Thank you, sir.
Thank you very much, Professor Munir. I think we came to the end of this first presentation. Thank you very much.